Good morning. Today I will discuss another important part of the acid base catalysis, which is also very simple, but you may not aware of this very important concept that is called alpha effect, or sometimes we call it alpha effect nucleophile. And this is not very old concept. It was established, I think, in the year of 1960, but it has tremendous applications in chemistry. Suppose there is some toxic chemicals or some chemical warfare agents, and that is very toxic. Sometimes we call it a neurotoxic, and you want to destroy these neurotoxic compounds. So generally you know that it is a one type of transformation, very toxic compounds to non-toxic compounds, and these are all chemical reactions. Some are nucleophilic substitution reaction, some are hydrolysis type of the reaction. Suppose we are able to discover some of the nucleophile which can increase the reactivity of any type of chemical reaction million times and billion times. So such type of application is based on the alpha effect. Before I go into details of the alpha effect, I just want to write some of the very simple as well as the complex type of compound, because actually the alpha effect was discovered by a very well-known scientist. His name is Professor William P. Jenks of course Brandeis University, USA. Actually he studied a very simple reaction, hydrolysis of para-nitrophenyl acetate with different types of nucleophile like cyanide, like OH, like pyridine, like aniline, as well as he has also taken some other type of nucleophile. Say for example, hydroxylamine, hydrazine, oxime, hypochlorite, hydroxyperoxide, and he observed that there is a difference in the rate constant. And deliberately, this is actually carboxylic ester, you all know, CH3CONH2, and this one is para-nitrodiphenyl phosphate. So it is carboxylic ester, it is called the phosphate ester. It is not very toxic. Now what is the similarity? Similarity is there that here is a group which is called the leaving group, is common. Here is also same type of leaving group. Then you might have heard about the two very toxic chemicals generally used as a pesticides and like that. One is paraxon. You can also write methyl paraxon as well as the ethyl paraxon. Another is the parathion, if this oxygen is replaced by the sulfur. Again, what is the common thing? Para-nitrophenyl acetate, this group is common. Para-nitrodiphenyl phosphate, this group is common, this group is common. So these are the some toxic chemicals, and as I have already told you that I want to destroy this chemicals with the help of some nucleophile. So, how do you explain the alpha effect? How do you explain the alpha effect? You all know regarding the alpha position. Now, scientific definition of alpha effect, just scientific definition, then I will explain the things. It is related to the nucleophilicity. Okay. Now, I can call it, suppose I write alpha effect. So, what is the definition? The increased nucleophilicity having, why? Suppose this is position, in adjacent there is a lone pair of electrons. There is also if I write one example, so it is alpha. Right, you can write. And you simply OH nucleophile, cyanide nucleophile. So just you see the difference. If I take this compound, again I am writing this. And you want to study, you just add simple sodium hydroxide OH. So it will form CH3, COO, nucleophile is added, and para-nitrophenoxide ion. So, and it will give a 400. So sometimes we can call it a leaving group. So what is the definition? Suppose I am just doing a chemical kinetic study of a para-nitrophenyl acetate in the presence of a normal nucleophile and same temperature, same condition, we have taken suppose hydrazine or another type of nucleophile, maybe hydroxylamine or oxime. I will give you some example, or oxime. So first, rate constant observed in the presence of normal nucleophile, you can write K of the normal. Okay. Then you repeat this experiment with the help of a nucleophiles having a lone pair electron in the alpha position adjacent to the reactive center. So that is called the, suppose, K alpha NE. You can write like NE. Now, if you compare the K alpha nuclei divided by K normal, there is a tremendous increase. In spite of tremendous research work on the alpha effect, still the exact mechanism is debated. Why? What is the reason for that? Whether it is due to the lone pair repulsion or stabilization of the transition state or single electron transfer. I'll explain step by step. So the first condition is that there must be a lone pair electron adjacent to the lone pair of electron on the alpha effect, alpha position adjacent to the most reactive center. Basically, whenever you study, suppose you are doing many times you do the reaction of methyl iodide reacts with some nucleophile, nucleophilic substitution reaction, and reactivity is based on the basicity. Suppose you are comparing hydroxyl ion and hydroxy peroxide. Of course, the basicity of hydroxyl ion is 50 times more basic than hydroperoxide ion. So that you thought that the reaction must be fast in the OH. That means there must be some anomaly between the reactivity and the basicity. So there must be some. So you see that increased nucleophilicity of an atom due to the presence of an adjacent atom with lone pair of electrons. Now I am giving some of the example. You might have heard about the Bronsted acid-base catalysis concept. According to Bronsted acid-base catalysis concept, if you plot a graph between rate constant and pKa of that particular species, there must be a straight line. And from that straight line, we can calculate the Bronsted slope. The value is almost, and there must be a linearity, less scattering. But if I take different types of alpha nucleophile, there is a tremendous scattering, and the value of this slope value will be entirely different. You can understand the things that is a normal nucleophile, but here is again lone pair of electrons. But with the help of molecular orbital theory, that problem can be solved. Now I am giving first, I have shown some of the example of esters, phosphate esters, carboxylic esters, some of the organophosphorus pesticides. Now I am showing some of the nucleophile which is called alpha, because the nucleophile showing the alpha effect is called alpha effect nucleophile. There is a possibility of small objective type question, MCQ question. The examiner may be given some of the nucleophile and you have to identify that which nucleophile is alpha effect nucleophile. So this is the example of hydrazine, hydroxylamine. Another is very important example of, I must tell you, that is called the oxime. You all know that there is a problem of organophosphate poison, because that organophosphate destroy our enzyme acetylcholinesterase. It's a phosphorylation process, because that phosphate group react with some active center of the enzyme. So now the question arises, what is the role of alpha nucleophile? It is chemistry. So if there is a phosphorylation process which destroys the activity of the enzyme, So we need some of the dephosphorylating process. So most of the alpha nucleophiles are reactivating oximes like pyridoxine. There are so many types of the oximes. So you must know the reactivity of the oxime. So this is one of the, I'll give the example what is oxime and how oxime acts as a reactivators, which can increase the activity of the enzyme. So sometime again the short answer type of the question, why alpha nucleophiles, or what is the application of alpha nucleophiles in biological system. So you can write that there are many types of oxime derivatives reactivators are available that can reactivate the activity of the enzyme. This is a very simple commercially available oxime, CH3CO, CH3NOH. Very simple type of the things. I can also like this is also one type of another type like that. Maybe one CH3. So this type of things is also there. So suppose I write ethyl peroxone. And this is called the leaving group, nucleophilicity. It is also ethyl peroxone, very toxic compound. Again CH3CO, alpha nucleophile. So you can write like that. So everywhere, why scientists are using this type of alpha nucleophile or this type of compound? Because everywhere there is a leaving group is same, and it is very easy to determine the reaction mechanism. You can very easily determine the rate constant. So, but in laboratory, we cannot use this toxic, although my research scholars are using peroxone and parathione. So what we do, we give them some simulants, that is called the simulants. That is not toxic. So in M.Sc classes, or you can using this type of simulant. So there is no, but if you figure out the reaction mechanism of the simulants with the help of alpha nucleophile and propose some of the mechanism, determine the half-life, so that mechanism could be used for the toxic compounds. And if you want to study the toxic compounds, yes, there is a laboratory like DRDO. Defense Research Development Establishment, Gwalior. So with the help of some precaution, one can study the reactivity of such type of toxic compounds. Sometimes it is called the chemical warfare agents like sarin, soman and tabul like this. So I can take some of the simulants. Simulants means that is not toxic, but the structure is almost same. Paranitrodiphenyl phosphate. Again plus nucleophile. So here again you see, sorry, here from here. Nucleophile may be joined with this type of the things. So again, and the alpha hydroxy depends upon this leaving group, that is called the nucleofugality. I will come to that point. So in a nutshell, you can understand that alpha nucleophile can increase the reactivity millions and billion times, so that in a fraction of second, suppose there is some toxic chemicals here or some chemical warfare agent lying on the floor, and if you have a very good nucleophile, so you can spray that alpha nucleophile, so within a fraction of second that compound can be destroyed. So that is the application of the alpha nucleophile. Now the origin of alpha nucleophile, why such type of things is happened, and how do you calculate or how do you know that this particular compound is alpha nucleophile? I am giving some of the known examples, but suppose you are doing some research and you want to figure out that this particular compound is alpha nucleophile, then you have to follow certain norms. First norms is that the comparison of rate constant of alpha nucleophile divided by rate constant of normal nucleophile, one case. Second, we plot a Bronsted catalysis law, pK of that alpha nucleophile and the rate constant, and determine there are so many examples. I am giving all these type of examples. Now I have given only one or two example of organic compound like hydrazine or amidoxime or oxime, hydroxamic acid, but in literature there are large number of alpha nucleophiles, and this is the research, because I am not an organic chemist, I am a physical chemist. So I do collaboration with some foreign scientists, organic scientists. They prepare different types of alpha nucleophile, send to us, and our research scholars do all types of kinetics. Yes, this is a very good alpha nucleophile. So the research is continuously going on, like hydroxybenzotriazole, IBA, like that. You can see that this is a point of research work, that people are working on the different types of alpha nucleophiles in order to discover the best nucleophile. Suppose I discovered a nucleophile whose half-life is 5 minutes. You just modify that compound so that half-life from 5 minutes to 1 second. So which one is better? 1 second is better. So that type of work is going on. Now, as I have already told you that it was discovered by Professor Jenks, but the alpha terminology was given by again Edwards, J.D. Edwards and Pearson. So when I teach you the scale of nucleophilicity, then I will explain the development of all these alpha. This is the first part of the alpha effect. What is alpha effect? Some of the example and origin of the alpha effect. Then there are some application of the alpha effect. I will explain. And there are so many scientists, the role of alpha effect, other things. And now this is very important. This point you must remember. What are the 4 important points by which you can say yes, this is the alpha effect. Number 1, as I told you, the alpha effect can be measured by the ratio of the rate constant, K divided by K normal. K alpha is that time when they studied, it was 2 to 10, but now it is 10 to the power 3, 10 to the power 4. Number 2, when you plot a graph between log K nucleophile and pKbH, so there is a larger for alpha nucleophile. Then the normal nucleophile, you know, if you study the Bronsted plot, it is like a very small value, 0.5 or 0.6. But if you plot a graph between the sum of the alpha nucleophiles and pKbH, so the value will be very high. Third point, always the alpha effect dependent on the nucleofugacity of the leaving group is a very important point. Here I am using very simple leaving group, para-nitrophenoxide ion. But in some cases, the leaving group may be different. Don't think that always you will get very simple. For the student purpose, for the research purpose, I am using simple para-nitrophenyl acetate, paraxon, parathion, and para-nitrodiphenyl phosphate. In all the cases, leaving group is same. But you can in future you can study other type of compounds, and there are a large number of research papers available. I will show some of the research paper after this class. So you will see that there are a large number of research papers. Even we also published a review article on the alpha effect. Me means my group, and also published a very good paper in the Royal Society of Chemistry journal, like Organic and Biomolecular Chemistry. It's a very prestigious journal. So first point is the relation between K divided by K normal. Second is the plot between rate constant using alpha nucleophile divided by the pKbH. Third, it depends upon the nucleofugacity. You don't have idea about the Hammett substituent constant or linear free energy relationship. It is also in your course. So after this alpha effect, I will explain this Hammett equation. That means suppose we are taking a para-nitrobenzoate, para-chlorobenzoate, para-fluorobenzoate, para-methylbenzoate, para-methoxybenzoate, and again studies their alkaline hydrolysis. And if you plot a graph between the rate constant, again pKh, so there may be a constant, sometimes it is called the reaction constant, like that. So again, if I apply the Hammett equation for the alpha nucleophile, it will be lower than for the normal nucleophiles. So there are 4 important aspects or the characteristic of alpha nucleophile. You can call this is a 4 characteristic of the alpha nucleophile. Again, it is for the short answer type of the question. Now, what are the origin of, this is the last part of this lecture, what is the origin of alpha effect? Why such type of tremendous increase in the reactivity? So again, there are 2 or 3. You have to remember all these 3 points. First point is that white natural, that there must be lone pair repulsion. There must be single electron transfer from HUMO to LUMO, that is also possible. There is the stabilization of the transition state and other things. So these are the origin of alpha effect. First is the increased polarization of the nucleophiles. Lone pair repulsion, or sometimes we can call it the electron-electron repulsion. Same thing. And of course, transition state stabilization by lone pair at alpha position. Relative stability of the products. And again, I think number 2 and number 5 is almost same. Ground state destabilization due to the electron-electron repulsion. And it is quite natural if you study normal reactions, methyl iodide or whatever you have taken, and there is of course nucleophile. Suppose I am taking the CH3I, so there is a partial positive charge developed on the C, partial negative charge, and nucleophile will directly attack with these things. And so you can remember 3 scientists. First is the W.P. Jenks, then Edwards, 1962, but one Israeli scientist, his name is Ghosh, S-H-O-Z, that is called the Ghosh. Ghosh proposed a simple model that is called the Ghosh model. That is the ultimate explanation of that alpha effect on the basis of molecular orbital diagram. So that is the last part of this alpha effect. So it is a small part, because if you see the course content of this this unit, there are a large number of other concepts like nucleophilicity scale, then linear synergy relationship, application of hard soft acid base theory. These are all, and lastly of course enzyme kinetics and other things. So the last model is called the Ghosh model, and as I told you that there are large number of research papers, and this is a very famous professor, and I have a very good correlation with this Professor Fountain, Keith Fountain of Truman State University, USA. He has published large number of research papers in organic chemistry, Journal of Organic, American Chemical Society journals. And but I have taken this diagram from this research paper, Journal of Organic Chemistry, published in 2006. But the main, as I told you, that this concept was based on the Ghosh model, and that was published in Journal of Organic Chemistry. So normally he has taken a, I think, hydroperoxide ion or hypochlorite ion. So this is a single electron transfer, and if it is a normal, so of course that is, if it is highest occupied molecular orbital, it is nucleophile, it must be electrophile, and it is of course lowest occupied molecular orbital. So this is the Ghosh model for the alpha effect. So very briefly, if I want to summarize you, that I have discussed the definition of alpha nucleophiles, and very briefly I have only used 4 types of nucleophile in this lecture. But don't think that there is only 4. I am using hydrazine, hydroxylamine, hydroxamic acid, oxime. Of course, hypochlorite is also there, hydroperoxide is also there, and deliberately I have using 2 simple reactions. One is para-nitrophenyl acetate, which can easily be remembered, which is a carboxylic ester, and second I have taken the example of phosphate ester, paraxone and parazone, and origin of alpha effect, and very preliminary information about the Ghosh model. In next class, I will discuss the linear free energy relationship, and that is called the Hammett equation. That is not Hammett acidity function. Hammett acidity function I have already discussed. So thank you very much.